about the transformation between the spherical coordinate systems and the Cartesian coordinate systems. And this is very useful. And let's see. And for spherical coordinate systems, and here let me address. So here is our JK. Okay, those are the unit vectors. If you know spherical coordinate system, and let me show that one here. Say, so that is a sphere, and then say if we have a point here, okay. So to do that one, basically we decompose it into this. So if this is a point onto a surface of a sphere which has a radius r, so basically here we have r, okay, and that's the first coordinate. And also the second coordinate is this. We want to measure what is the longitude, theta. The third coordinate for spherical coordinate system is the latitude. And the latitude here, they have two the common exercise. Either you can use this angle, okay, or the other options, let me draw that one here. So the same thing, the same point here. So we have the first coordinates and second coordinates, and the third one is people like to measure that one from here to here. Okay, so you can see the third coordinate, and the people have a different preference. So here, sometimes people define this as a phi, and sometimes people like to use phi is like this. So basically, r theta phi, r theta phi are the three coordinates used in the spherical coordinate systems. And sometimes people like to arrange into r phi theta and etc. Depends on the people's reference. So next time when you have chance to go take a look at any textbook about the coordinate system, the spherical coordinate system, then you have to be careful about what kind of the arrangement they're using, because they have the kind of the right formula for kind of something that could be different from other textbooks if they use a different arrangement of the coordinates. Okay, so that is the one I found a little bit, it's not so consistent among the textbook. Okay, so beware of this one. So here we see. So now in my notations for these 6 nodes, I'm going to talk about the 2 scenarios individually and give you the complete description of the transformation matrix and see. Okay, so the first one I think I will try is go to this case. Okay, so for my note, so let me draw this one carefully. So here, let me only show portions. So for example, the point is here, and sorry, should be light. So here, let me define this is the unit vectors, and let me call IR. Okay, that means a unit vector in the radial directions, and oh my goodness, I made a mistake. Sorry. made mistake in drawing. Let me redraw that one. So here I need to define this is the theta, okay? And a point is here. So this is the radius r. So let me define this is IR. That is in radial directions. So that's the unit vectors. Okay, and then the second one, I want to define the tangential unit vector, which means tangent to the point downwards. So that is, let me define that is the unit vectors, and let me call it I. So say, let me define this angle is phi. So this is the tangent to in the direction of phi. So let me define these vectors I phi. And the third one is I'm going to draw is at this point. Basically, is tangent to the longitudinal directions. So here, the IR, I phi, and the third one constitute a Cartesian, locally Cartesian coordinate system. So here, let me call this is I theta. Okay. So that is the one, and right now our goal is to find out what is the relation between IJK and IR, I phi, I theta. Okay, so that is our learning things. So from here, we need to know how can we do a successive a series of the transformation to get the from IJK to IR phi theta. So here we can try. Rotation sequence, and here is the summary. We first rotate about 3 axes, which is k axis by an angle theta, and then follow up with rotation about the 2 axes, which is j axis by an angle phi. And let me explain this one in detail. Okay, so that is the quick notations. So step 1. I'm going to explain this one. Okay, so let me draw this one. So IJK. So right now we're going to rotate about the third axis about theta. So which means we're going to rotate this one about theta. Okay, so let me put that one drawing into the. Didn't just use them. Okay, so here the theta is not arbitrary. The theta is the coordinate we use here. So whatever the spherical coordinate system, the coordinate theta here, you apply that theta to here about these rotations. So now let me say this is the say one coordinate systems. Okay. So this is the say given notation. So say right now I align. So right now in this way align, you can see basically this is the in the theta direction. Limit for this is the theta directions. Okay. So from that rotation, can you see that I theta basically is aligned to this direction? This one basically is in tangent. Basic tangent, my drawing is not so perfect. Basic tangent is in that directions. Okay, so that is I theta. Okay, this one will need a little bit kind of the imaginations from you, and we rotate. And this one, let me arbitrary. Let me say this is I1. I just arbitrarily give a numbers here. Okay, give a symbol here. Okay, so for this case, we have the matrix. From our old is x YZ. And for our new, so that is say for the new, and that is the say the first coordinate and the second coordinate, and then I theta and z, and the third one is z coordinates. Okay, so this one representing the coordinate in this direction, theta represents the coordinates in that direction, etc. So now for this case, we look at this one. We simply express individual vectors into the system. So here, let me focus on this one. So this is a one axis. So that is expressed in terms of ij. From here, you can see that is cosine theta. X, y, z, and sine theta 0, right? Right now, I simply decompose this one into two vectors, into two components. So this is cosine theta. This is sine theta. Okay. And now for the theta, in a similar way, projecting into I, the axis is minus sine theta. This is cosine theta 0. And z basically in this axis, that is the same with before, so that's 0 to 1. So let me call this is R1 matrix. Okay. And now step 2. We're going to rotate about the two axes about D. So right now here I'm going to base upon. Let me redraw this one. So here, this is our new coordinate system. Let me write it out here. I theta axis, and this is the K still axis, and this one is our I1 axis. Okay. So right now I copy this red one to here, and the second step is to rotate the second axis about by angle phi. So that means is by an angle phi, follow up, the phi is not arbitrary, the phi is going in that direction. So that means here we're going to rotate about phi in that direction. So under this case, this one will be so let me build up this one. So that is a plane about which we so this is this plane. So hopefully you know if this is the I theta axis. So right now simply it will rotate by this. Okay, so here is I theta axis. This paper represents it described is this hatch plane. So here is simply will rotate is by this. Okay, so right now from here, this is phi, and this is phi. So right now we can write it out here. From the old 1 theta z to the new. So right now from here to the new, and under these situations, this one will be aligned to IP here. So that one, this is IP. Okay, and this one will be aligned to IR. And that is the sequence will bring us to align to the final destinations of this one. So right now we simply write it down here. So from here, theta keep the same. So here is our I theta. Okay, so here is our theta, and then here for the third axis move to R. So z axis move to R here, and for the first axis move to I phi. So that is our phi here. Okay, now we simply write it up for this axis, and that is in terms of 1 and theta. So right now in terms of 1 and theta, that is cosine phi and minus sine Right now, again, projecting this one, this amount is cosine phi. This amount is in I1 direction, so cosine phi in one direction. And now the second amount is the sine phi. The sine phi is in which direction? In the k direction. So in the old z direction, so that is minus sine phi here. Okay. And for the second coordinate, and that is the same as before. So here we don't have any projection here. And for theta, that is the same as the before, so we don't have anything. And the same thing, you apply the projection of the second component, you can find out that should be minus sine phi, 0, and cosine phi. Okay, so here this is our transformation matrix, let me call it R2. So therefore, for this case, for these options, let me summarize and say if we have a coordinate phi, theta r, and that should be equal to R2, R1 times XYZ. Okay. So if you have the Cartesian coordinate system, say any point here, so say if this point is 1, 2, 3, if you want to transform to get what is corresponding R value, theta value, and phi theta value, plug into this formula. And let me implement the R2 should be equal to cosine theta, cosine phi, minus sine theta, cosine theta, sine phi, XYZ. And let me write it up here. So sine theta, cosine phi, cosine theta, sine theta, sine phi, and minus sine theta, 0, cosine phi. Okay, so if you want to implement symbolically, and that is one, but otherwise I would recommend you start from here, because in MATLAB you can very easily calculate these multiplications very easily. But this one is for your reference. Next time coming back here, we're going to finish the second case. Monday we have our test, first test, and then we follow up, continue on Wednesday. Okay, thank you.